Welcome back to the Learning Studio. You're watching our mathematics series in the section on data, algorithms, and computation, where we explore the math that powers modern computing, optimization, and AI. If you're new here, don't forget to follow us by clicking the link below. And remember, the full playlist is in the description so you can catch up on all our previous episodes. Today's topic is a big one: algorithmic complexity and computability. The mathematics that defines not just how fast algorithms run, but whether some problems can even be solved at all. Let's start with a simple question. Imagine you want to solve a giant Sudoku puzzle or crack a code. Computers can check possibilities quickly, but what if the number of possibilities grows so fast that even the most powerful supercomputer in the world would take billions of years? This is the heart of algorithmic complexity, understanding which problems are easy, which are hard, and which might be impossible to solve efficiently. Core concepts explained simply. Here are the essentials. P versus NP problem. Problems in class P can be solved efficiently in polynomial time. Problems in class NP can be verified quickly, but not necessarily solved quickly. The million-dollar question: is P equal to NP? If true, countless hard problems could suddenly become solvable, with huge consequences for cryptography, optimization, and AI. Big O notation. This is the language of complexity, describing how the runtime of an algorithm grows with input size. Linear, quadratic, exponential, each step up changes what's practical. Computability. Some problems are beyond algorithms altogether. No machine, no matter how powerful, can solve them. These are called undecidable problems, like the famous halting problem. Efficiency in AI. Training a neural network, running reinforcement learning, or optimizing a massive dataset, all of these depend on algorithmic complexity. The efficiency of AI models is directly tied to how smartly we handle computational limits. Why it matters in AI, computing, and technology. Algorithmic complexity and computability define the boundaries of technology. In AI, efficiency determines whether a model can be trained in hours, weeks, or not at all. In cryptography, NP-hard problems keep our digital world secure. In optimization, understanding complexity tells us which problems need clever approximations rather than brute force. In theory of computation, it shows us the frontier between what machines can achieve and what lies forever out of reach. In short, it's the mathematics that tells us not only how to build smarter algorithms, but also where to stop dreaming and where new paradigms, like quantum computing, might be required. So, algorithmic complexity and computability is about more than speed. It's about the very limits of problem solving. It's the difference between the solvable and the unsolvable, between efficient AI models and impossible ones. In our next episode, we'll move into something very practical and powerful: matrix factorization and tensor decomposition, the math behind recommender systems, natural language processing, and some of the most successful algorithms in data science. Don't forget to follow us by clicking the link below and check out the full playlist in the description. This series is building a roadmap from abstract mathematics to cutting-edge AI, and every step unlocks something new.